Thanks for having me. Thanks for the introduction. So I'm going to start. My talk is going to be about 7 algorithms for the same task. It's a very theoretical talk, so hopefully I will give some motivation. But if at some point you have questions or anything, please feel free to interrupt me. Or if I say something that is unclear or you have any question, basically. I have to start with a disclaimer. I do not actually know the name of those 7 dwarfs. I know them in French, but it's not the same. So I can't actually do that. So there is no test at the end about those either. But so in order to start, the goal of this presentation is to provide you with some algorithms to test if data is uniformly distributed. So what does that mean and why do we care? So the whole thing is basically in some kind of statistical setting or observations where you've got n identically distributed and independent samples from some unknown distribution. And I'm going to assume that that distribution is over a discrete set of size k, which is the first big assumption I make because, in real life, a lot of things are actually continuous. But, you measure things, there is some quantization. So even if you quantize things very finely, you still have a finite set of possible outcomes. And so this is one of the motivations. K is really large. Let's say you measure things very accurately, so you have a lot of possible outcomes. So the alphabet size, K, the domain size, is really, really large. And the question you want to ask is, well, is that data basically uniformly distributed on that large domain, or is it statistically far from this? So already there are several things we might want to ask here. It's like, why uniform? Why does that matter? And what does it mean to be statistically far from the uniform distribution? So again, why the uniform distribution? Coming from theoretical computer science, I have 2 answers to that. The first one is, well, if you can't do this one, there is no chance you can do anything more complicated. Uniform is pretty simple. So if you can't address that question, well, the rest is probably going to be harder. The second one, which is also kind of computer science, is like, well, the uniform distribution is actually also in a very specific sense the hardest. There is a formal way, I'm going to get back to that, that says like, oh, if you want to actually test whether your distribution is like something you have in mind, which is, I don't know, bimodal, or is it like a binomial distribution, or is it like a zip flow with some parameters, you can reduce that to the uniform distribution in a very formal sense. So you can use one or any of those algorithms for that more general question. So again, it's as simple as it gets, and it's also as hard as it gets. In terms of the distance, I'm going to use total variation distance. I'm going to define that a bit later, which has a bunch of properties, but one of them is it's a non-trivial distance. The guarantees it gives are very strong. It is an actual distance. It satisfies triangle inequality. It satisfies a lot of things you really want to have that, for example, some other distance measures don't have. Kullback-Leigh blur can be unbounded, doesn't have the triangle inequality. Divergences in general don't. I just say it is bounded, and it's also weirdly related to other things you might care about. So it's related to other distance like L2 via Cauchy-Schwarz and also some other inequalities. It's related to KL divergence and chi-square distance via things like Pinsker inequality. So it's nice. It has a lot of properties we want, but also it's related to other things that you might care about. So that's the intro slide. I hope I convinced you at least of something like this. Now, in terms of applications, why would I care about whether my data is uniformly distributed or, like, let's say, satisfies a model I have in mind in general? So that's basically the goodness of fit question. One possibility would be, oh, you have some algorithms, or you have some other things that, performs well on this type of data, performs very, very badly on some other, and you want to use that to do model selection, to select the best model so that you can use the right tool after that. So that's one of the motivations. And as a result, one thing that's important here, like you want to do that decision question, is it uniform or not? Is it this thing I have in mind or not? Very quickly, because otherwise, if that step is already very slow and requires a lot of data, there's no real savings you will get. The other motivation here is purely in a statistical sense. You want to know, like someone comes to you saying, I've got a model that explains the observations from the real world, for example, or I simulate this process and I claim it satisfies this distribution. You want to check this. So you want to check whether it's true or like, no, it's wrong in a noticeable way. So those are possible motivations for this. Okay, I said there was no test about the dwarfs, but there is a small test here. So I think those are actual draws from actual distributions. Some of them are uniform, some of them are not. The domain size is 50, so not even that huge. And which ones come from uniform distributions? Which ones come from something that is far from uniform? So I guess we could all agree that this one, the yellow one, is probably from the uniform distribution. It looks kind of uniform. The one from the top left, the purple one, probably not uniform. That's like there is some pattern that definitely looks weird. But the two at the bottom, it's actually not that clear, right? Because you do have some random fluctuations. You have finite samples, a finite number of samples. You can't be sure about anything there. This might be consistent with random fluctuations, which brings me to like one of the issues. One very natural approach to test this would be just to compute the empirical distribution. I've got n samples. I can compute the empirical distribution on n samples, look at it, and be like, okay, does this look uniform or not? And the main issue with this approach is that for the empirical distribution on n samples to actually converge close enough to that to the true underlying distribution for me to make that call accurately, I would need to take a number of samples n that basically is linear in the domain size k, which might be good, but is a lot. Again, think of k as a very, very large parameter. And the name of the game is, can I do something while taking a number of observations that is strictly negligible or much less than the actual domain size? What I want essentially is to be able to do that testing task much faster than the number of samples I would need to learn the distribution. Because it's supposed to be a simpler problem and it's supposed to be something I can do as a preliminary thing. So I promised you I would define what the total variation distance is, because that's kind of central here. This is that thing. So there are two definitions. The first one is, well, the actual definition, it's the supremum over all possible measurable sets. It's a finite alphabet, so everything is measurable, of like the probability given on that set by one of the two distributions P minus the probability given on that set by the other Q. What that means essentially is like it's related to the best test you could get given one sample. What's the best way you can distinguish between those two possibilities? I give you one sample. I say it either comes from P or from Q. What's your best probability of being correct? And the total variation distance is related to basically the type 1 and type 2 error on that. The other definition that is often very convenient is just, well, it's, look, you have two discrete distributions, they're over k elements. Look at that as a vector. It's a vector of numbers. They're non-negative, they sum to 1. Well, the total variation distance is exactly half the L1 distance between those two vectors. It's not obvious. It takes maybe like 10 lines to prove given the other definition, but it's often very convenient to have. So this is total variation distance. And again, it's the measure of how distinguishable two distributions are given one observation. It fully characterizes that. So given that, our goal is to get a testing algorithm that is given an input. Let's call that epsilon, a small, think of the epsilon as being like a small constant or something small. And NIID, so again, independent identically distributed samples from some unknown distribution P over a domain of size K. And that algorithm needs to say either accept or reject and satisfy the two following things. If the distribution is actually uniform, if P is equal to U, then it better say accept with some high probability, let's say 99%. So type 1 error. If the total variation distance is between P and the uniform distribution is at least epsilon, so like far from the uniform distribution, then it should reject with probability at least 99%. So this is what we ask. If you see this, you probably have at least one question. It's like, why 99%? What is this magical number? And there is, I'm going to get back to that, but basically it's completely arbitrary. I can replace that by any constant. Coming from theoretical computer science, I tend to ignore the constant factors. And so that's very convenient for me to put constants. I don't really care about on slides. So as I said, if I can do uniformity testing, I can do the more general question, which is called in my community identity testing, which is instead of uniform, you come to me saying like, here's a specific distribution I have in mind. Oh, it's binomial, like it's the binomial distribution with these parameters, or it's actually just like these strange things where like the probability to see element 17 in this is 0.23, the probability to see element 400 is 0.1, etc. Anything that you know explicitly, and you want to test whether the unknown distribution is equal to that. So it's actually equivalent. If I can do uniformity testing, I can do the other one as using the algorithm as a black box. And of course, if I can do the more general question, I can specialize it to the uniformity, to the uniform distribution as well. So in some strong sense, they're equivalent. The 99% probability of success is completely arbitrary. You can replace that by delta, or small delta if you want, and all the results will go through, but you basically, like there's a standard way to go from one to the other. You pay a multiplicative factor, something like logarithmic in 1 over delta in the number of samples you need to get. I'm not going to go into the details, but it's called the median trick. And it's basically run the same test many times on fresh samples, take the majority output. If the majority of the tests say accept, you accept. If the majority of the tests say reject, you reject. And you can boost the probability of success that way. It's not necessarily exactly the optimal thing to do, but that's good enough. Now, also, I said we want to do something that is better than let's just learn the distribution and see what happens. So learning the distribution entirely up to total variation distance epsilon would have a dependence on k, which is linear, k over epsilon squared. Turns out for the testing version, which is just tell me if it's uniform or far from it, we can do much better, and it grows as square root k over epsilon squared, and that's optimal. So I don't know if there's any question about that square root k, but you can think of that as, think of the birthday paradox, essentially. Unless you've seen at least square root k observations, even if it is uniform, you will never see the same element twice. So basically, you have no actionable information at this point. You just saw a bunch of things, each of them once, and you cannot tell me if it's, oh, it is uniform, or it's actually like uniform on a subset of the domain of size half the domain. In both cases, you will not have seen any element twice, so you can't really distinguish between that. So square root k is a lower bound on the number of samples you need at least that. And turns out you can also, as soon as you start seeing the same thing twice, you have a sufficient statistic that you can use. I'm gonna get back to this, but keep in mind the baseline, like the right answer should be, I can solve this problem with square root k, with n is equal to square root k over epsilon squared. And I possibly put some not so huge constant in front of that square root k. So does anybody have any idea about how one could approach this? Sorry, I know I don't mean to put you on the spot, but if anybody has an idea of like what would be a reasonable approach to testing uniformity, or testing if the distribution is uniform or far from it, now is the time. After that, I'm going to give you 7 of those. So not all reasonable. All right. Again, it's a bit hard when put on the spot, so I'm going to give you one idea. As I said, once you start having more than square root k observations, okay, so there's a question like the central limit. There is an observation, the central limit. So that's something that actually is quite important. Yeah, so the central limit theorem will tell you something, and more generally, a lot of the analysis, I mean, this is not a new problem, right? Statisticians have been considering that kind of things for 140 years, something like this. So there are a lot of tests that we know, you know, goodness of it, like the chi-square test and so on. The issue with all those tests, at least the way we learn them in statistics, is they tell you something about the limiting distribution, meaning n goes to infinity. And that gives you a lot of information about those. All that we know that, oh, this test as n goes to infinity will actually solve the problem and like solve it optimally. And we know exactly like how the statistic behaves, we have its distribution, we can compute a lot of things. We can compute like confidence intervals, we can compute all that. But it's as n goes to infinity. And the issue with n goes to infinity is like, if I give you 1,000 observations, you have no idea based on those results whether it's enough to say anything. It's not in the limit. The tests I'm gonna mention here are better in the sense that they give you information even for finite sample. So given n is equal to 1,000, you can basically look at like the complexity of the problem and like get the epsilon you can say something about. So works for finite, gives you finite sample guarantee. That's great. But they have an inconvenient as well. They also tell you a lot less. They don't tell you anything about the distribution of the test statistic. They don't by themselves allow you to say anything about the confidence intervals, or all they tell you is like, if this is uniform, then I will accept with 99% probability, or like 99.99. And if it's far, then I will reject with that probability, but no less, no more. So, okay, there's another suggestion, bootstrapping. Okay, given what I said about the birthday paradox, one of the options would just be, well, as I said, before you take square root of domain size samples, you don't see anything twice. After that, you start under the uniform distribution, seeing things twice. So maybe just count the number of things you've seen at least twice and be like, if it were the uniform distribution, I should see that many collisions, things that I see twice, number of observations that take the same value, pairs of samples that take the same value, under the uniform distribution, and then try to relate that, like, oh, if it was far from uniform, maybe I should see fewer of those or more of those, something like this. So that's basically one of the ideas. We're going to see, the first one is going to take counting collisions and see what happens. Before
Michael
that,
Small, Clément, Michael Small has put another example suggestion in the chat.
Mm-hmm. Oh, yes.
Bootstrapping, shuffling will test against IIDness. You could computationally simulate uniformity with the same mean and test against that. Oh,
yeah. Okay. So I here, like, I do assume things are IID. So just to, if I understood correctly, like, I don't want to test whether things are IID or not. I assume that everything I'm going to say, if your observations are not actually IID, I mean, the analysis doesn't go through. So then you would have to do extra work ahead of time to mitigate this. Like, the big assumption I make is your observations are IID. I want to test whether they come from the uniform distribution or not. But if they're not IID, roughly half of what I'm going to mention is going to fail. Or I would have to quantify how they deviate from being independent. So I'm going to mention a few algorithms to test whether things are uniform, but as in every case, it's hard to quantify how good an algorithm is, right? I'm going to just say like, oh, this algorithm like achieves, like answers the question taking like n of this size. So, oh, it's optimal or not, but you might care about a lot of other things. So this is just data efficiency. How much data do I need to conclude? But there's a time efficiency, which you might care or not about, but you might also have a way to compute the answers very fast. That is something that you have to keep in mind. Memory efficiency. So, if actually your observations are taken by distributed device or like, sensors that you deploy in the field, you will really, really need to deal with the fact that these devices might be memory limited. They can't perform, arbitrary computation that take a lot of space. If your data comes as a stream, think of that as, well, I keep observing TCP/IP packets or things like that, and I see them once at a time, and I have to do the thing fast, and I have limited working memory. Again, like in a streaming setting like that, you might want to make sure that your algorithm is memory efficient. So maybe it can't even store the whole data set. It has to like maintain a small sketch of it. There's a simplicity in the sense of like very complicated algorithms often lead to very complicated things to implement, and also very prone to mistakes things to implement. So a simple algorithm is usually better to implement, better to understand, better to extend and generalize. A few moving pieces is always good. Also, there is a simplicity, but from the analysis point of view, nobody wants to read 70 pages of proof to understand if something is correct or not. First of all, because it's horrendous, but also because that makes things really, really hard to like extend. Ideally, I want to use that proof or that argument to do something else. The shorter, the better. There's also robustness. So here, the way I frame the problem, it's very, very limited. I said like, it is either exactly uniform or it is far from uniform. Well, nothing is exactly uniform, right? Like there's always some kind of noise, some measurement issues. So the actual problem you might want to solve is a robust version. Is it close to uniform or is it far from uniform? That's a much harder problem. But you can, depending on how you define close, you can still do something. So like, is it like kind of uniform or really far from it? You might want those robustness guarantees. And some of those algorithms will provide that off the hook. So just like, oh, it's actually giving like close enough to uniform versus far to from uniform for free. There's also the elegance of the algorithm. I teach algorithms. So I know that some of the algorithms I teach are very clunky, look horrible. I would not recommend anybody actually just like spend too much time on them. But some of them are also very nice and elegant, and it feels like a joy just to understand this algorithm. So it's very subjective, but it's also something that is nice when you have an algorithm and you feel it's the right one for a task. And the last one is generalizable, because as I said, this is an algorithm for a particular task, testing uniformity. You might want to generalize to something else. What if I want to test uniformity, but given that extra thing? So an example is, that's relevant more to my work and research, is privacy. Maybe the data I actually analyze is private data, sensitive data. So then I want the output of the test not to reveal anything about any of the particular data points I've observed. There's a way to quantify that. It's many ways, but one of them is differential privacy. So it would be nice if an algorithm I have to test uniformity allowed me to just like do a little bit of a tweak, and then suddenly it also gives me something that satisfies privacy. Or it would be nice if I take this algorithm and just because of some extra property it has, it's also something that I can use in another setting, or I can use to get extra guarantees that were not part of the original problem formulation. So that's what I mean by generalizable. So, okay, here are the 7 algorithms I'm going to mention, if I have time, but I might skip over some of them. The first one is the collision-based. So it's basically counting the number of things I see twice, and then compare that to the uniform distribution. So you can, it's an idea that's very simple and very natural. If your motivation is like, oh, the birthday paradox says I don't see collisions, so I can't do anything. And then like, well, if I see collisions, maybe I can do something. The issue is the analysis is a bit tricky. It's very easy to get some proof of correctness. It's very hard to get the right one, and then that becomes kind of annoying, and the details are not nice. The other one is unique elements. So it's exactly the opposite. The uniform distribution is the one for which I will see a lot of unique elements. At some point, I will see collisions, but before I will only see elements once. Every time I take a new sample, it's probably going to be a new one, a new element of the domain that I discover. So maybe I can just count how many unique elements I have among my n samples and be like, oh, if it's large enough, that should be uniform. So that's also a very natural idea. That's kind of dual to the first idea. It has one limitation, which is like the distance parameter is basically like cannot be too small. And the reason for that is pretty simple. If n is too large, at some point, if n is much, much, much larger than the domain size, I will see every element at least twice, even under the uniform distribution. And then the test is basically not giving me no information. The third one is the statistics chi-square test, slightly modified, but very, very little. And it's just, it's something that I guess we all know and love. And turns out it works and gives those finite sample guarantees, even if you just need to analyze it in a way different. So there is no real drawback for that one. It's simple and it works, and it's comforting. The fourth one is also very nice and natural, but very surprising to me. It's doing exactly the thing I said would not work a few slides ago. I take all my samples, I compute the empirical distribution. It looks like something. Since I'm taking much fewer samples than the whole domain size, there are a lot of holes in this distribution, a lot of things that I've never seen. But then I just compute the distance of that thing to the actual uniform distribution. So I can compute that explicitly. And then I say like, well, here's what it should be if it was actually uniform. I can analyze this. Well, here's what it should be if it was far from uniform. I can also, I mean, someone, not me, but can actually analyze that. So the people from that paper, GPP 18 did. And then like, hopefully there is some difference between the two that allows me to conclude. So that's a bit surprising. That gives a very biased, counterintuitive way to analyze things, but that works. The random binary hashing, so I don't know how many of you are familiar with hashing, or like it's a very nice idea for a lot of algorithms. Just basically random, you have a domain of a large size, K. K is very large. This is really annoying. Just take that large domain and convert it in something much smaller. Or small, well, let's say 2 elements. We should be able to deal something over 2 elements when K is equal to 2. What does it mean? Map that to this. It's just like each element will become either 1 or 2 randomly. So I choose randomly where to map each element. So equivalently, I partition my domain uniformly at random in two sets, and I just project my data on that. So that's binary hashing. I hash all my elements to only a domain of size 2. And then, well, at that point, I just do whatever I can on this. And that works. It's not optimal, but that's very fast and very easy to implement as well. And we're going to see if we get to the last two. They're probably not as important. They're variations of something before. So, okay. I'm going to go a bit fast over some of those, but I want to give a few insights about, what is the basis for those algorithms, and hopefully that's going to also give you a bit of insights about the techniques that are used for that. If you have any questions, I actually have written a survey on all of this, so I'm happy to point you to that reference. It's free. I'm not trying to make royalties out of that. So, and I'm happy to provide references and pointers after this. So one of the insights is that total variation distance is nice, but it's not so nice. So we want to test in that L1 total variation distance. But it has a lot of drawbacks. The analysis is hard because essentially every time you try to do an analysis of a lot of things, L1 distances are a mess. They don't behave nicely. What is nice usually is L2 distance for various reasons. So maybe we can map one to the other. And there is something like there is an obvious way to go from one to the other is Cauchy-Schwarz inequality. It seems very loose, but what it's saying is basically, well, the distance between two vectors in L1 is upper-bounded by Cauchy-Schwarz by the L2 distance times square root of K, because the domain is of size K. So basically, this is a very loose inequality, but it gives something. And we can use it to see the following, right? If the distribution is actually uniform, then the distance to uniform is 0. And regardless of the norm I'm considering, like this is still going to be 0. So if I'm actually uniform, the L2 distance is also 0. If the L1 distance if the total variation distance is at least epsilon, then by that Cauchy-Schwarz inequality, the L2 distance is at least, well, epsilon over square root K. There's a factor 2 somewhere, but 2 epsilon over square root K. So that's, at least that's something. And maybe that's enough. Now, this says that maybe I can use L2 distance as a proxy for the thing I really care about, L1. There's another reason for which I might want to care about this. There's that magical fact that is specific to L2 distance and specific to the uniform distribution, which is why the uniform distribution is so nice. It just, if I look at the L2 distance squared between the uniform distribution and my unknown probability distribution, this is literally this thing I wrote here. There's a square in the middle. Squares are nice. I can expand them. So no, I expand the square. And then there's a magical cancellation that happens. And this is equal to this thing. You can check. It's not hard to show. It's actually pretty immediate, but I get this, which is basically like the L2 norm squared of that distribution minus something that, I mean, it's just a thing that doesn't depend on the distribution, just 1 over k. So what this is saying is like to estimate this thing I want to get a handle on, it's enough for me to estimate this thing to sufficient accuracy. And okay, why is that good? It's because this thing here has a very, very natural interpretation, which is that, again, I find it kind of cool fact, which is if I have a distribution and I take two independent samples, what is the probability to have a collision? I keep saying the word collision, so probably it matters. So you take two independent rows from some unknown distribution P, what is the probability that the two values are equal? And you can check, since those two things are independent, you get this. And this is exactly that quantity I want to estimate. So the squared L2 norm of the distribution is something that is commonly known as the collision probability for that distribution. It's also, if people want like another thing, it's also related to like the Rayleigh entropy of order 2. It's like if you take the log, but I don't really care about that myself. But collision probability is nice to understand. So that suggests that that test I hinted at before, take a bunch of samples, compute the number of times you see a collision, should give me something about this. Because again, if I can estimate this accurately enough, then by this equation, I can estimate this accurately enough. And by this one, if I can estimate this accurately enough, I can distinguish between it's 0 and it's at least epsilon over square root k. So that gives me the first test, which is count collisions. I take n samples, and then here's my unbiased estimator. For all of the n samples, I look at all the pairs and I check whether they collide. I count the number of pairs that collide. So two samples collide if they actually take the same value. And I normalize by n choose 2 because that's the number of pairs I have. And that gives me an unbiased estimator for this. Now I will threshold that appropriately, meaning like I want to distinguish whether it's 0 or at least, so I look at the square, so at least 4 epsilon square over k. So I need to threshold that somewhere in the middle, and hopefully I can actually distinguish between the two. So I would argue that's very simple. I just need, it's a very simple statistic to compute. It's kind of, it's really fast. I mean, it's a linear, like it's a quadratic time algorithm as stated, but you can make that linear time or almost linear time. It's kind of intuitive if you rely on the previous 3 slides. It's somewhat elegant, or at least not too inelegant. The analysis is not that simple, unfortunately. The reason is, so here's what we want to do. We compute this thing, we threshold it at like something around basically the gap between the uniform case and far from uniform case to distinguish between the two. One classical way to do that is just, I have the expectation, I know the expectation, what the expectation should be. I've got a sum of things. I'm going to compute the variance and use Chebyshev's inequality, for example, to argue that things are close enough to their variance with high probability that I can distinguish between the two cases. And the issue is Chebyshev's, like computing the variance of a sum of independent things is really easy. I mean, it's just the sum of the variances. But these things are not independent. They're not pairwise independent, etc. Because I look at all possible pairs to see if there's a collision. And you know, if observation 1 and 2 take the same value, and observation 1 and 3 take the same value, well, I know for a fact that observation 2 and 3 take the same value. You know, you've got those kind of dependencies that creep in. Handling them is a bit of not a nightmare, but takes a couple pages of proof. So it's not as nice to analyze as one would want, but it does work. The second one I promised, again, please interrupt me if there's any question about this. So again, it's simple, but hard to analyze. It's simple to implement, hard to analyze. The other one would be, maybe I don't want to look at collisions. I just want to count the number of things I see exactly once. The expectation, it's not an unbiased estimator for the L2 norm squared. the expectation is not hard to compute, but it's not nice to look at either. This is this thing. So now what I want to argue is like under the uniform case, it is something, when it's far from uniform, it's something noticeably different. And hopefully I can do the same kind of trick, compute the variance or something so that, and show that they concentrate around the expected values so that I can distinguish between the two cases. That's basically what a lot of those tests are about. Prove that between the uniform case and the far from uniform case, the expectations, there's a gap. And then analyze the variance to say that if I take enough samples, then my statistic will concentrate around the expectation well enough that that gap is preserved. And so I can do a threshold between the two values and use that as my rule. So under the uniform distribution, I'm going to make a bunch of approximations, but using the fact approximating 1 minus x to the n by 1 minus n times x, for x small enough. Under the uniform distribution, the expectation is roughly this thing, n minus n squared over k. Under the same approximation, which is not a valid approximation in many cases, if it's far from uniform, I will get n minus n squared times that L2 norm squared. So at least this seems reasonable. I should get some kind of gap as well. And so I get that gap between the two expectations as well. Now, the issue is this is actually not a valid approximation to do. So actually proving that this is true takes more effort. But then assuming this, and assuming I can prove the variance is small enough, I've got some gap between the two expectations. I can use Chebyshev's inequality again. And if you do the computation, you will see that you need n square, like you will need n to be square root k over epsilon square again. So this does work. And again, if you forget about the fact that the proof is not that nice, this is a pretty simple algorithm. Take a bunch of observations, count the ones you see exactly once, like the values you see exactly once among those, and compare to some threshold you have. If it's below the threshold, you say far from uniform. If it's above the threshold, say it's uniform. So that's pretty fast. There's some issue, as I mentioned. It only works in some parameter regime, which might be good enough. But if epsilon is too small, then what happens is square root k over epsilon square. So the number of samples I take becomes too large. It becomes much larger than the domain size. And in particular, using some kind of like coupon collector argument, I will have seen all elements of the domain at least twice, which is bad because then that test gives me literally zero information whatsoever. Count the number of things I see exactly once. If the answer is 0, that doesn't tell me much about what I should do. So that's a small caveat for this one. In the next 10 minutes, I want at least to cover this one because this is one that probably you've seen in statistics. The idea beyond the chi-square test is essentially to say that there is a notion of distance between distributions. It's called the chi-square divergence. It has a bunch of properties. It's a thing called an F divergence. It's related to KL divergence and total variation distance between kind of simple inequalities. And it has a nice form that hints there is a test you could extract from here. So in particular, here's a test. Hopefully it looks familiar to you. I kind of renormalized it and did some kind of strange things, but it's basically computing the empirical chi-squared divergence between things. And here I use Ni to say I've got k elements in my domain. Ni is the number of times among my n samples I've seen element I. So I'll just compute this thing. There's a small correction term here because I'm not actually, I'm going to use something, say like, oh, instead of taking exactly n samples, I'm going to take like, first draw some Poisson random variable with parameter n. I get some value n big, like let's call that n prime, and then I take n prime samples. This is just for convenience of the analysis because then a lot of things become independent. That's a nice trick to know. And so I can actually analyze that better. But then I have to have that correction bias, that correction term, so that it's an unbiased estimator. Then computing the expectation is pretty simple. It gives this thing. Oh, great. That's a very good estimate for that L2 norm square. That is the thing I care about again. So I can also compute the variance. It's actually not too hard this time. I use, I guess by now, like it looks like I'm a one-trick pony. I use Chebyshev's inequality to say that, oh, the variance is small enough. The expectation, there is a gap between the two expectations in the uniform and non-uniform case. So by Chebyshev's inequality, basically the gap in expectation is larger than the square root of the variance. Things are going to concentrate around their expectation. That's good enough for me to be able to distinguish between the two cases with high probability, high constant probability. So we can do the same here, and that works. So this is very nice and comforting, at least, you know, things that seem reasonable in the statistics class and have seemed reasonable for the past 100 years or so, well, actually they work and they're optimal even for that, even in that finite sample regime. It has some disadvantages in the, like, you know, you remember that big table I had at the beginning, like, does it generalize or not? It is very sensitive to outliers and things like this, but this is for the sake of testing uniformity. That's okay. This one is the one I said did not work, then I said work. So this is the plugin estimator. Take n samples, compute the empirical distribution on those n samples, see how far it is from the uniform distribution and act accordingly. So this is a very natural idea, you know. The issue is that obviously that doesn't work, right? Because if I take a number of samples that's much smaller than the domain size, most of the things I won't see even once. So the total variation distance between that empirical estimate and the uniform distribution is going to be almost maximum. It's going to be 1 minus something negligible, which is bad, right? Even when my distribution is actually uniform, this statistic is pretty much as bad as it gets. It doesn't look like I can do a lot of things. As it turns out, it's still good enough. When it's uniform, it's very close to 1. When it's far from uniform, it's very close to 1. The key is that very close is not the same. It's very close and like very close, but slightly larger. So there is actually a very, very small gap between the two. Analyzing that gap is a bit of a nightmare. I'm glad I didn't do that, but it does work. And so again, that's kind of comforting because take the empirical and compute things on it seems like a very natural idea. For this one, you need a lot more than Chebyshev's inequality, but it's a pretty fairly complicated paper. Maybe not as simply written as it could be, but even there. So that's this one. So it's simple, it's fast. I would say it's not intuitive because for maybe 15 years, people were convinced it didn't work. So it's not just me. It is elegant and it generalizes in some nice ways. So again, what I mentioned about like extension to other settings. So one disadvantage of everything we've seen so far, except this one, is they're basically using L2. Right? This one does not use the L2 norm as a proxy. Every other thing used L2 norm as a proxy. What is a characteristic of L2 norm is basically it's very sensitive to outliers, or put differently, like it's very brittle to changes in your data. It's not Lipschitz basically in changing your data point. This one is L1, much more robust to outliers, which is great for example, that privacy application I mentioned. So this actually provides a lot of room to extend it to sensitive data or things like that, because basically it's not sensitive to outliers. So as a result, what that means is like it doesn't depend on any particular data point too much. It's basically L1 instead of quadratic in the sample counts. So it's not sensitive to any particular data point. That's exactly what I want if I want to be able to argue that it doesn't reveal too much about any particular person's data, for example. So that's a very nice feature of this algorithm. And finally, in the next 2 minutes, I'm going to skip over the last two, but I just want to mention the binary hashing because it gives something suboptimal in terms of data size, but it also has a lot of nice generalizations. So the main issue since the beginning was K, the domain size is large. if the domain size was small, let's say 2, this is just, I give you a coin and I ask you, is it biased coin or is it a fair coin? And I mean, we know the answer to this one. I think if we didn't know by now, it would be pretty concerning. So we know that to distinguish between like it's fair or it has bias at least alpha, we can do that with one of our alpha square samples, and it's tight, and like we even have like more like refined bounds of some sort. So if we could just use this, then we would be good. And let's just make this, right? So I've got that giant domain size. I'm just going to partition it at random in 2. I look at each data point. If it falls in the first set, I say it's a tail. If it falls in the other set, I say it heads. So I can convert all my data points in just binary things. Now, if the data was actually uniform, well, I divided it in sets of size 2, in sets of same size. So if it was uniform, then it's a fair coin. The key is proving that if it was not uniform, then it's a bias coin. And what is the bias? And you can actually prove that. It's not that horrendous to prove, that basically there is a bias, small bias, but some bias. And now once you have that, you can use the previous fact. So it's either a fair coin or bias with bias alpha is equal to epsilon over square root k. So you need 1 over alpha square that gives you that sample complexity k over epsilon square. So that's simple, basically pick a hash function, or if you could divide your domain in 2 halves. It's not quite equivalent, but both work. It's fast. It uses very little memory. It's kind of fun to analyze. It's not optimal. But again, it generalizes in some settings for which it is optimal. So again, like some privacy application for a different notion of privacy, this is the right thing to do, actually. It's called local privacy. I'm happy to elaborate on that after. So I just wanted to mention this one because an idea that seems way too simple, actually, well, is still nice and has some non-trivial applications. So I just mentioned privacy. It also has, if I can say another keyword, it also gives an optimal algorithm for quantum testing of uniformity. I think the last slide, I defined a problem. I argued it was important. Maybe you believe me or not. If not, well, at least I hope you didn't find that too boring. If you believe me it's important, then like why having 7 algorithms for this? And actually, there's probably a few I've missed. And the reason is not all algorithms are optimal in any direction you want. There are a lot of things you might want to think of when you implement or use an algorithm. All the stuff that is the fine print or things that are like kind of implicit. So you have to take all those things into account. They don't give all the same guarantees. They don't extend all the same ways to things you might care about. And that matters. So always be mindful, even if 2 things seem to give the same result, maybe one of them is actually much more useful to you than the other. I guess that's kind of the upshot there. And yeah, with that, I'm going to stop. If there are any questions, I'm happy to answer.